A coaxial cable consists of an inner cylinder with radius A and an outer tube with inner radius B and outer radius C. Both the cylinder and the tube are conductors. The cylinder is carrying a current I and the tube is carrying a current of the same magnitude and opposite direction. Let's use Ampere's law to find an expression for the magnitude of the magnetic field in between the cylinder and the tube. Here's a circular path in between the inner cylinder and the outer tube. The circular path has radius r. R is in between A and B. And Ampere's law says the line integral of magnetic field along a closed path is equal to mu 0 times enclosed current within that path. So let's apply Ampere's law to this situation. Along the circular path, B is uniform because we're always at the same distance r from the center of the cylinder, and B is always tangent to the circular path. So the line integral simply becomes B times circumference of the circular path, which is B times 2 pi r. And the enclosed current is simply capital I. So then we said B times 2 pi r equals mu 0 I. We isolate B, we get B equals mu 0 I divided by 2 pi r. Now let's do the same calculation for the region outside of the tube where r is greater than C. In this region, I enclosed is the sum of the current passing through the cylinder and the current passing through the tube. These two currents have the same magnitude and opposite directions, so they add up to 0. I enclosed is equal to 0 in the region r greater than C, meaning the right hand side of our equation becomes equal to 0. And the left hand side is still equal to B times 2 pi r. R is our distance variable following the circular path, the line integral of B along that circular path. So then we get B equal to 0 for the region outside of the tube.